Okay, so let's get started. So where were we? Okay, introduction of deep networks, right? And we had given the very basics of the graphs, the weighted graphs that are used to represent deep networks, generally a DAG, not always, but generally. So very basic concept still. We talked about representing very simple functions, right? So for example, I think that we were discussing a 3-variable function like this. I think we did xy plus z, right? And now we were at x plus y times z. So what happens when I want to compute the derivative of a function, right? So in general, if I have a function, say, in that case, I can call these q, for example. So I can say then s, my output, is equal to q times z, okay? Right? So now I want to compute the partial derivative of s with respect to x, let's say, right? This variable right here, x. And how do I do that? I don't know how to do that, but what I can do is I can certainly compute the partial derivative of s with respect to q, right? I can do that. And I can compute the partial derivative of q with respect to x, right? So I can do that. And obviously, I can also compute the partial derivative of s with respect to z, right? That's an easy one. This is equal to, anyone? The partial derivative of s with respect to z? Q, very good. And now what's this equal to? Anyone understand the homework? What's this equal to? You can do it right now, right? It's not that hard. So we have q here, and we take a partial derivative with respect to x. So this is equal to this first component. What's that? Okay, so what's this first component? 1, and then this z, so this is z. Very good. So, whoops. So anyways, this leads to this, right? Right. And this use of the chain rule, right? Here we're using nothing else than the chain rule. This use of the chain rule is what's known as backpropagation, okay? Or in the literature, you'll also see as backprop for short. Any questions about this? No? Okay. So we can now generalize this, obviously, to multivariate variables, right? So in general, we don't have these simplistic cases, but we'd rather have variables defined in some feature space of higher dimensionality, right? So for example, we can say x is defined in a space of p dimensions, and y in a space of q dimensions, and so on, right? And then if I have a function, right, or a vector rather, y, my vector y is equal to, let's say, y is a function g of my input x, let's say, right? And now I have an embedding of functions, remember, that I keep embedding one function after another, right? That's the idea of deep learning. So I could have, say, z equals f of, whoops, not x, but y now. So f y, and I add the arrow as always to indicate that this is a vector, okay? So again, if I want to compute the partial derivative of z with respect to x, I can do that, but I need to do that. This is z. I need to do that in some more intelligent way, and I'm going to do the same thing I did before, but what I'm going to do is I'm going to do it for each of the x sub i's, right? So if I have x is defined in a space of p dimensions, I have x sub 1 through xp, so I'm going to add over all j the partial derivative of z over yj times the partial derivative of yj over xi, right? Or if you prefer, I can write this as we have always done for nonlinear least squares methods as a gradient, right? The gradient of my variable x, or with respect to x rather. So this is going to be the partial derivative of my vector y with respect to my vector x times the gradient with respect to y. And what's this called? Again, we've used this like 100 times now. The Jacobian matrix, right? So I have here the Jacobian matrix that I can use to compute the gradients, right? And again, if I have z vector now, from now on, unless I say the opposite, right, I'm referring to my x, y, z's, w's, whatever it is, as vectors, which is the general case. If I want to do this, and this is given by, say, z over y times y over x, and say x over w, that means that I'm computing the derivative of the function with respect to y, derivative of the function with respect to x, the derivative of the function with respect of w, which you could also write this term as this one here, which is f prime of f of w, right? Am I missing one? Right? So I'm just taking the partial derivative of y, which is equal to f of x, which is equal, x is equal to f of w, right? So I can keep embedding these things. And then the second one is a partial derivative of x, which is f of w, right? And the last one, it's just f of w, right? Make sense? So that's really what we're doing. We're solving for this embedding that we have. So let's see this backpropagation algorithm. Now to apply backpropagation numerically, when we run this through our function, right, or our functions rather, and we change the parameters of these functions, right, to get a better result, we have to run this numerically. So how are we going to do that? We're going to do two passes, as we've always done, like in other graph methods that we define or other nonlinear methods that we defined, right? So in the first pass, that's a forward path. So we're going forward in the network. And by forward, remember, this is a directed acyclic graph that has directed edges. So by forward, I mean I follow the direction of the edge of the arrows, right, of the edges. So the edges point from the beginning to the end of the graph. So this is the forward path. And then I'll do the back path, which is against the direction of these arrows. Okay. So forward first. I'll call this the forward propagation. So if I have my loss function L, if I have my loss function L of say y hat y, right? This is the loss function I want to compute. Y hat is the output that I have, right? That my embedding of functions, right? So if I have f of f of f, right? Many times up to the last one, right? If I have my embedding, okay? Y hat is the output that I obtain with, well, actually, this is incorrect, isn't it? This will have the parameters, right? Okay. So with this current parameter set, this is the output I get, right? And the loss function, what does it do? It compares that current estimate of the output with the true output, right? So-called sometimes the oracle, or if you have an oracle function, that means that you know the underlying function that converts one thing to the other, right? Or at least you know it for some values of that function, right? So you might have, remember, you might have a set of xi's inputs and yi's outputs, say 1 through n, right? And xi's will be in some feature space of p dimensions, and yi's will be, let's see, if yi's are, if we use yi's in classification, what would that be? What's that?
Like 0 to 9.
Right, a certain set of numbers, right? So it could be the natural numbers, or you could define this with the natural numbers. You could define this with z. You could define this with some set that of finite or infinite number of categories that you may want to define. I guess you could define it with the real numbers also, but sort of weird that you would go to a set that large. And so this is for classification. And for regression, then yi is in some space of q dimensions, right? And q could be 1, obviously, if it's regression, but it could be 1, 2, 3, whatever it is, right? Okay. Now, also remember that it is very common to make these loss functions stable. And for that, we add the regularizing term here, right? Some regularizer that gives us a stability to the computations that we're going to perform. That's actually very important to have, as we showed in regression. Now, remember that, or note that in general, a deep network like this one is nothing else than a regression function, right? As always, all we are doing is we have a desirable output, we have a known set of inputs, and we're looking for this functional mapping, right? From x to y, right? That's what we're really looking for, right? And the same that we did in regression, in rich regression, for example, which add that regularizer to stabilize the solution and to make it computable when we don't have enough samples as well, right, that do not represent the whole space. Instead of having to use PCA to eliminate the null space, we can just regularize our loss function, right? Okay. So let's see the algorithm. Again, X the input, Y the output, or the target output if you prefer. We set our parameters, W. Okay. This would be a capital W because it's the weight matrix of our graphs, right? The adjacency matrix that has all the weights. And I have I in, say, 1 through, I don't know, L. And those weight matrices define the model, right? This is the definition of our model, this plus the functions, obviously. Set, also, we need to set our biases, B. So I'm going to have this also 1 through L. L, the number of layers or combinations that I might have of these functions. So these are the biases. And I have to determine or set the H phi that I want to use, right? The mapping function. And now what I'm going to do is for L1 through, I'm sorry, L, let's use K. From K1 through L, I want to do, let's see, I'll compute AK equal to BK, right? The, set parenthesis maybe, the bias for this first element, right? Plus the weight matrix for that node. So the weight matrix for that node, which would be capital WK times whatever function I'm using here, say K. I'm going to use K minus 1 to represent that I have that function at the beginning of this process, right? But if you prefer to use K, it's the same thing. It's just notation. And then I'm going to set the next one, K, as F, right? The function of A, K. Make sense? Yeah? So all I'm doing, I'm applying my base classifier, right? Linear base classifier, right? With a bias, with the weight vectors, right? And that function up to that function or of the embedding of functions up to that position in the embedding, right? And then I move, I compute that output, and then I move, and I keep repeating that for every embedded function, right? So I end the 4 here. And now at the end, my y hat is going to be equal to the last h that I have computed. And my J matrix is going to be the loss function of y hat and y plus some lambda, right, times the regularizer, given the parameters of our function theta. Okay? Any questions thus far? Okay, so now we can do the same thing but going backwards. So now I'm going back through that same embedding of functions. So to do that, now I need to start computing the partial derivatives, right? So I need to, from this J matrix, I need to compute the gradient of J first with respect to the output, right? Variable, y hat, times L, y hat L. And now I'm going to assign this to some variable, let's say g. And now again, as before, I'm going to do a for loop. Okay, now I'm going not 1 through L, but L through 1, right? I'm going backwards, okay. So L through 1. And I'm going to now compute at each step, same thing as this, the gradient of j. But now here, this was the very last one, y hat, which is the output. Now here, what am I going to use? What output am I going to use? The output of that node, which is called here AK. So with respect to AK here. So this I can define as G product, element-wise product with f prime of AK, right? And what else do I need? So I need to assign this to G for my next step. And what else do I need to compute? Oh, I need to compute, I know. I need to compute also, not only with respect to A, but also with respect to B, right? So I also have the gradient with respect to B of J, which is equal to G plus lambda, the gradient of my regularizer. And now G is going to be this gradient of H at k minus 1, J, which is given as capital W K transpose times G. Okay. And note that all I did is I did that same process but backwards, right? So when I compute H here, right, at the very end, right, this gradient of H is with respect to that function, and I am computing the gradient, right, with respect to first the function, then the biases, and then the A's, right? Which is the opposite of what I did here, right? I did A, B, H. Make sense? Okay. And N4. And what else? We're done, right? So I have finished my iterations. Okay, so let's see maybe a quick example of this. To see how this works. Now, please do review these things. Try to implement them for small graphs now to understand how these things work. Because as these graphs grow, it becomes increasingly difficult to understand what is going on, okay? And I wish there was a very nice theory I could teach you about how these things work and how to make them work. But as I mentioned in the previous lecture, we don't have that, right? So this is pretty much trial and error. So we're entering uncharted territory here. So let's see. I'm going to start with maybe a variable x and a variable w. Let's make this small. Maybe x, I'm going to define it in 2 dimensions. 2 dimensions here. Actually, I'm going to make this 3 dimensions. such that I have x1, x2, and w1, 2, and 3, right? And let's see, I could probably do, I'm going to do x1 and x2, and I'm going to have a function in this node, right? This function is going to be an addition as we had before, right? You can write an addition here. You can write, maybe, if you prefer, f1. And you can say f1 of ab is equal a plus b, right? Right? I used a and b already, so why don't I use f1 of uv, u plus v, right? Same thing. And now I'm going to add some weights here, so I could add w1 and w2, right? So here at the output, what do I really compute? I compute x1 w1 plus x2 w2, right? Make sense? Okay. So that's one way to see that. Maybe I could then have this output now. I want to say do this. I'm going to add a 1 here. And I'm going to still use f1. And I'm going to add my w3 here. So now what output do I have here? Now I have, let's see, x1 w1 plus x2 w2 plus w3, right? And so on. You can keep doing this kind of things. Maybe what we're going to do next is we're going to add another node with another function, f2. Let's say that f2 of u is equal to the exponential of negative u. How about that? Right? Or e to the power of negative u. How about that? Okay. Or actually, let's make it even more interesting. How about EU? And now I add a negative sign here, right? So here now at the output, I have e to the negative of this thing that I had computed, which is x1 w1 plus x2 w2 plus w3, right? You see how this works? Now for small graphs, I can see what I'm doing. For huge graphs, when this gets really deep, I mean, you could still theoretically compute what it does, but mostly you're just going to have an idea of what's going on, right? So this big network, some of these big networks will end up having millions of nodes, right? So with millions of nodes, you cannot write this down analytically, but you can say, okay, this, what is usually done is you could have blocks like this, right? Like this one here. And then we call this F, right? And then you say, okay, this node has 3 inputs, and it has 1 output, and it looks like this, or actually 2 inputs, because this is a 1, and 1 output, right? And that's what it does. This is the function. And then this, you use it as a block in the network, okay? You see what I'm saying? And then, for example, now I can take this function, f, right, that I have computed here. I'm going to take this out because this is not an input. I don't want to confuse you because this is fixed to 1. So now I can have my inputs like this, x1, x2, and I have my output that is equal to this, right? So this is equal to f of x1, x2, given my weights w1, w2, w3, right? So these are my parameters here, right? Okay. And now, for example, I could go ahead and add this to another function, say g1, where g1, maybe I'm going to say that g1, given an input u, outputs 1 plus u. Okay. How about that? And maybe I can have then this send through another function, g2, where g2 is 1 over u, right? And so on. You can start combine this. You could also take this and send it through another f, the exact same f, right? So now you're taking that output. If we call this output s, now what's this? Well, I need one more. So let's say x1 here and s. Then what's this output going to be? It's going to be e to the negative x1 w1 plus this one s w2 plus w3, right? You see that? And so on. When you do this, though, note that these parameters that I'm defining here, right? Where did I write this? I wrote this somewhere. Oh, here, right? These parameters that I'm defining, right, are for a specific k, right? Specific layer or node that I'm working with, right? So the parameters, if I keep repeating this block, the parameters are going to change from layer to layer. Make sense? Right? Because if I have here this f, and then that's sent to another f with some inputs here, and to another f here, meaning that f that I computed there, right? x1, x2, x3, x4. Then the parameters here, right? The parameters for this particular node and for this particular one and for this particular one are obviously going to be different, okay? Okay. All right. So please do look into this. Please look into understanding the forward path, the backward path to compute the values, right? So you can easily implement this. Now, eventually, you don't have to implement this if you don't want to. So Shanli already talked in the recitation, I think, about how to use PyTorch, right? Or any other system that you like to use. And all these systems have all these algorithms already implemented in them, right? They have many of these functions that we're going to define today already implemented. They have backpropagation already implemented, right? But it makes sense to try to implement these functions in MATLAB to begin with, or in Python, because they're very straightforward and it will help you. And then what you can do is you can run them numerically through a simple network like this, right? And then, because for simple networks like this or graphs like this, you can actually analytically compute the partial derivative, right? You know what the result should be. And then if you apply this numerically, meaning that you use certain numbers here and here for the parameters. And for the inputs, you know what the forward and the backward path are going to give you, right? And then you can make sure that you're implementing the right thing. Okay. It's important that you do this now, because as I said, when this grows, it becomes increasingly complicated, increasingly difficult, almost impossible. Yes?
Since we have the type for the data like float or double or single, for each step, when we calculate the gradient using chain rule, we will accumulate the inaccuracies layer by layer.
No.
It seems for the first 7 layers after the backpropagation, will that be reliable?
That's a good question. Remember what I said in our last lecture? I said, don't compute, whatever you can, don't compute your derivatives numerically. Compute them analytically. Because if you can compute them analytically, you avoid these problems, right? The more you rely on numerical precision, the more you will run into issues. So, I mean, obviously computers do have enough precision these days to give you a decent result, but that is an issue. That's a very important problem. We'll get to that. Now, backpropagation by itself, as I've described it here, does not work for big networks. It's too simplistic. So there are optimization methods. I'm not going to cover in detail, obviously. I'm just going to mention them, but because this is covered in optimization optimization courses. But there are optimization algorithms that are much better, much more robust for very large networks, okay, than this basic one. All right. Any other questions? Yes, back there.
Deep learning libraries implement the networks as for loops?
Oh, you mean PyTorch, for example?
Yeah.
Or
what's the speed difference of you implementing for loops versus...
Oh, I see. So it depends which libraries you're using, and you have to read the details of the function, of every function that you're going to use. Because some of these functions are optimized for CPUs, and some functions are optimized for GPUs, right? And it depends what you're using. You're going to be using one function or another. When these networks grow really large, there is no CPU. I mean, you could run it in a CPU, but it'll take forever, no matter how powerful that CPU is. Then you just have to use GPUs. But GPU only makes sense if the code is optimized for that GPU. Otherwise, yeah, it'll go a little faster maybe, but you're not going to make huge gains. So you want to make sure that everything has been parallelized to the maximum. And again, there are people that are just dedicated to building these libraries, right? To building PyTorch or whatever other system that you like to use, because it takes a lot of effort to do these things. And what we're going to do at the end is we're going to use things like this, right? We're going to use blocks and say, okay, this is called function like PCA, right? PCA is a function that you can use in MATLAB, right? Okay, so when you're going to use PCA in your algorithms, you're not going to re-implement PCA. It's already been optimized for you where you ever do that. So that's the same thing, right? We're going to use these optimized implementations. Now, the newer also the functions or the tools that you use, the less optimized they tend to be in those libraries, obviously. Right? And it also depends on who maintains these libraries. So some of these, or most, if not all of these systems started in the university, at several universities around the country. And now they have moved into companies, right? Companies basically acquired those softwares, and they maintain them. And obviously, if there is a big company behind it, it's much more likely that they're going to spend the resources that are required to keep this up to date. Right? People like PyTorch these days because people like Python a lot. So it has a lot of good things, or a lot of good properties. MATLAB is really moving into deep learning too, so they are including a lot of libraries. So I think that is also going to be competitive. But just because, MATLAB used to be the platform to know in machine learning, computer vision, speech analysis, and all this. But these days, Python is just like almost as good or better, I would say, than MATLAB, honestly. Okay, more questions? So let's move on. So one of the questions that you will find when you are using these backpropagation algorithms in networks like this is that you may be using functions here. These functions that I have used thus far are conveniently differentiable, right? But I could come up with a function f, what was the number? Was that 2? So f3 of uv, for example, could be the maximum of u and v. Whoops. Now I can do the forward path easily, but how about the backward path? Now I can still do the backward path numerically, right? Because I can just compute what it would correspond to in the early stage to get me the result that I have at the output. So that I can still do, but I cannot do that analytically unless I linearize, if possible, my function, right? And this is an option. I can make the function differentiable by finding a surrogate function that is differentiable, that actually approximates what I'm doing here, right? So whenever that's possible, I tend to like to do that because then I can still solve it analytically, and that has advantages. But if not, you're just left to the devices of the system. Okay. The other problem with this algorithm is that the Jacobian matrix that you need to compute, right? To compute this Jacobian matrix, that Jacobian matrix may be huge, and I mean huge, right? So one solution is to only compute the diagonal of the Jacobian and use the chain rule to work all the different areas, all the other different areas. So that's a solution. It saves space, computational space and time. So that's one way to solve this. Again, the libraries have really good implementations of that. It also depends on which algorithm or set of what computer or set of computers or GPUs you use. If you want to use really large networks, I mean, one thing is use, but train, right? I mean, backpropagation, we're defining this because we want to learn the parameters as we've been doing, right? With a nonlinear list of squares, we want to optimize the parameters of our regressor so that the output is what we expect it to be. So if you want to train a large network in your home computer, good luck. I mean, you have to be really, really patient. Maybe in a few months, you're going to get some results, right? I mean, these things are huge. You need really big computational power, right? Okay. So anyways, backpropagation, again, you have the output y hat, you have the desirable output, and you keep iterating this, right, until your parameters theta gives you the output that you want. Now, functions that you'll see implemented in these libraries that we were just mentioning, certain functions like this one that I described here, which is just a random function that I wrote down, I came up with. Standard functions that people use, and therefore, because they are standard and people use them, they are implemented in all the libraries of any system that you may want to use, like PyTorch, or the logistic sigmoidal function. Now, the sigmoidal used to be the function to use for neural networks in the 70s, 80s, and even the 90s. Okay. And as you know, the sigmoidal of x is equal to 1 plus e to the negative x. And that looks something like this. Okay, well, that's not very good, is it? All right, how about this? That's a little better. Okay, right? That's how it looks. And what else? 10H. This is it used to be very popular. It was the second most popular after sigmoidal. Not used that much recently, except for a very particular type of network that is called a GAN, a generative adversarial network, and we'll get to that later on. GANs still use 10H, okay? And the 10H of X is, or looks something like this. It's very similar to the sigmoidal, but it has an advantage, and that's one of the problems of the sigmoidal. One of the problems with the sigmoidal, why it doesn't work real well, especially with backpropagation, is that it's not mean-centered or zero-centered. Okay, so the computations are not as stable as a 10H that looks something like this, right? So as I said, for some types of networks, 10H is still very much used. The most popular function that you'll see out there, which is the one that I will recommend that you use almost every single time, especially if you are interested in classification, is called ReLU, Rectify Linear Unit. That's what it means. And that's just basically the one I wrote down here, but it's the maximum of 0 and whatever input x, right, I have, right? So the ReLU of x, it's equal to the maximum of 0 or x. And that therefore looks something like this. Let's see. If x is positive, I'm in this quadrant, right? This is x. This is the output, the ReLU. So if this is positive, this is x, so that looks like this. Okay. Hold on. Let's see if that works. That looks something like this, right? And again, this would be, as with the other ones, this is x. This would be the ReLU. This is x. This is the sigmoidal. And this is x. And this is the 10H, right? And if it's 0, meaning on this side, then I'm 0, negative on this side, then I select 0 as the output, so this looks something like that, right? There is a variant of the ReLU, which is called leaky ReLU. And this is equal to the max of 0x, but then here, instead of 0, you're going to add some parameter. Let me call it, let me do it more general. This is going to be maybe a function of g, right? But keep that very small, right? So it could be an epsilon, for example, or it could be a function that grows with x, but it's still a small. So the point is that it should look something like this. This is the same. And for negative numbers, it's going to look something like this, right? Very small, but there's going to be an increase here. Yes?
For backpropagation, we need a differential function, but at 0.0,
Well, if it's 0, then numerically it's 0, right? So you're not running into problems numerically. When you backpropagate, it's 0. You're just not moving forward. And that's actually counterintuitive, but that's actually what helps learning big networks. That's why ReLU is so popular in deep networks. It actually helps. I know. All right, other questions? So these are popular functions that are already implemented. Of course, you can build whatever function that you want, right? It's up to you. Only that then, if it's not implemented in the library, you have to implement it yourself, right? Not a big deal. You can do it. And now optimizing it for a GPU and these things may be trickier, but implementing any function is something you are definitely able to do. And the reason, I cannot emphasize this enough, the reason why these are the main functions that people use is because these are the ones that have been shown to work for the type of things that we're going to do next, okay? All right, no questions? So let's move on to our first type of deep networks that we're going to talk about. And this one is called convolutional neural networks. So we have two things that we need to define. First is, all right, we talk about what a neural network is. What is it? It's a graph, right? A weighted graph, typically a directed acyclic weighted graph. Fine. We said that we can have our weights. We can have different functions that I apply here, right? In general, note that these functions are going to be nonlinear. These are the functions that will add nonlinearities into our system, because obviously everything else that we define is a basic base linear classifier, right? W transpose X plus B, right? The bias and the normal of the hyperplane. So if you add now nonlinearities here, you can, as we have done with kernels, right? You can find nonlinear hyperplanes for classification and nonlinear manifolds for regression. Fair enough. But now it comes to the point of, all right, how are we going to put these things together? What are we going to do, right? And there's no manual for that, right? So you just have to, like a Lego, you're given these pieces, and you have to put them together, right? And I want to talk about the different pieces that people use to put these things together because it seems to sort of work. And convolutional neural networks in particular is one way to do this. And what convolutional neural networks do, they're actually inspired by the mammalian visual system. Okay? So back in the 60s, 70s maybe, Hubble and Wiesel, who won the Nobel Prize for their work, were studying the early visual system of the cat. Okay? And the way they did this is that was high-tech technology at the time. Now this is done in multiple research labs around the world with many animals, including humans. You would open the skull and place electrodes to read the firing of the network of the cells of the neurons in the brain. Okay, and then you anesthetize the animal first before you do that, and you look a little. Then you close everything, right? And then you present the stimuli to the animal, right? And then the animal responds to that stimuli, and by responding, these neurons fire, and then you record the firing of these neurons, and then you try to decipher what this firing means by finding the correlations, right, between what you show and what happens internally in the network or in the neurons. And Hubble and Wiesel, what they did is they were showing light points on a dark platform and rays of light, right, or bands of light on that blackboard, so to speak. Okay, and then they were moving this in multiple positions, either the dots or the lines in multiple positions on that blackboard, and then they were recording the different cells at different positions in the early visual cortex of the cat. And what they found is striking. They found several things. First, neurons in early visual cortex are organized in a matrix such that each location of that matrix corresponds to a visual part of your visual field, right? So in your retina, if you consider your retina is curved, but if you flatten this out and it would make it look like a matrix, right? An area of that retina corresponds to an area of the cells in early visual cortex. And there is a one-to-one correspondence, right? It's not as simple as a one-to-one because obviously there's more cells that represent the fovea. If you have taken my image processing and or my computer vision class, you'll know that. The fovea, which is the center area of your retina, right? Your retina. So the eye looks something like this. Okay. No, it does not. Okay, so here's your lens, maybe here, or the iris, the lens, it's back here. And then here, you have a lot of sensors, okay? So this is a cross-section, what's called a lateral, right? Or sagittal cross-section of the eye. And if you have an object here, right, say something like this, right? Then the light travels through your lens and then gets projected, onto the back of your retina, right? And here you have neuron cells that read codes and rods that read that information, pre-process it, and send it to the back of the brain. So your brain looks something like this. Okay, and this is the back, this is the front, and this gets sent to the back. And there's processing here, right, in the retina. You're actually processing information in the retina. There's another area that this goes through, which is a subcortical area, which is called the LGN. Don't write this down. All the details are not important. I see some people writing it down. Like, don't. And there's more pre-processing here and more processing here. And this area in the back of the brain is called the early visual cortex, right? So all this is early visual processing that occurs. And what they find out is first that there is this early processing that corresponds to one-to-one, right? Obviously, you have more sensors in this region here that I drew that goes through, the rays that go through the center of the eye project into this area, which is called the fovea, okay? And that's where you have most of the sensors. And the more you go to the periphery, the less sensors you have. So actually, the resolution out here in your visual field is much, much lower than the one at the center. Now, of course, you don't see it that way because your brain always lies to you, right? And it gives you the impression that everything is nice, in the same way that it gives you the impression that all that you see is in color, when in fact only the fovea has color vision. There are some color senses in the periphery, but it's almost zero, right? So you don't see color vision in the periphery. So this is the illusion that the brain gives to you, and all this is done after early visual cortex. This is later processing. All this processing is beyond conscious control, right? So we are not aware of what this processing is like. Our consciousness doesn't have access to it. So what they notice again is that this first processing just detects when the light either goes on or goes off, when there is a change, but not when there is just an activation, a constant activation, right? And that was very interesting because that actually shows that we respond to change, not to constant illumination, right? And the same is true for all the other senses, right? So that's the first interesting thing. The other thing is that these sensors are based on, are center surrounded, meaning that if you activate the center of the sensor or the censored area and not activate the surrounding area, then the neuron fires. But if you activate both or deactivate both, then the cell does not fire, right? So if there is light here and there isn't light here, then you're fine. But if there's light here and there is also light here, then the cell does not fire, right? And so on and so forth, right? They prove also that as you go deeper into that network of cells, the next layer depends on this previous processing, right? So the first processing, you can detect dots. The second processing level, by combining these center-surrounded cells, you can detect lines. At the next level, you can combine these different lines that define different orientations to detect just a line independent of orientation, and so on, right? So based on this idea, some computational people in the 70s derived a model for a neural network, computational neural network, that looks like that, derived by, or found rather, by Hubble and Wiesel. And that network looks something like this. Now, it's only a gross approximation for a variety of reasons. Number one, our cameras don't have more resolution in the fovea than the periphery. They have equal sensors of color sensors in the periphery than in the fovea, and so on, right? There's not even concept of fovea in an image. And our cameras respond to constant illumination, not change of illumination, right? So, okay, with these caveats, there's another caveat, obviously, that I've mentioned already, that we're going to define these networks as direct directed acyclic weighted graphs. And in fact, the brain, the mammalian brain, and even the other animal's brain is highly cyclic, right? So it actually has as many connections going in the opposite direction, right? So actually in the human brain, you have more connections going from higher order areas of the brain, right? That may be here or here, going in that direction toward the early visual cortex, that you have connections going in this direction, okay? So it's highly studied, this pathway that goes from the retina through the LGN to the early visual cortex and then all down here. This is called the ventral pathway of visual perception. And this is highly studied. We know very well how this works, right? But there is another one that goes backwards that is much less understood, right? And that's not, in humans, that's not even the only pathway, right? Because there's another pathway that goes from the retina to another subcortical area. It's called the superior colliculus. And from this area, it goes directly to some higher order areas in this region of the brain that's called the temporal lobe. So you can imagine this is just super complicated, right, in the human brain. You had a question?
Yeah, on those backwards moving weights, would it be the activation from the previous iteration?
So we don't really know, but the idea, the models that we speculate may be true is that in the brain, okay, here in higher order areas, you have models, okay? Now, these models could be a model that you have learned of your environment or of the people that you know. It could be models that are innate to your brain that allow you to function in the world. When you are born in this world, all the information that the sensors give you are highly redundant, right? So in computer vision, if you've taken my classes, you will see that for every image I give you, there's an infinite number of possible 3D worlds that could have generated that 2D image. So how on earth are you going to interpret the 3D world? It's an impossible task. Well, not if you have a model, internal model, or a set of hypotheses or a set of assumptions that are embedded into your system that allow you to solve this, right? So that is one of the hypotheses, that this is sending what's called top-down information to solve the problem, okay? Compared to this stream, which is called bottom-up, okay? All right, so the way this works then is we are going to take a patch here, right, a window of that image, and we are going to process this using a convolution, right? We're going to apply a convolution to this, and this convolution is going to give me a result, right? So this here is a convolution. And this is going to give me a result. And if I apply this throughout the image, right, by convolving a kernel, right, I'm going to select some kernel, and I apply this throughout the image, right, a simple convolution, then I'm going to end up with another image here, right? So this will have as many pixels as this one. I'm just drawing it smaller, but it's the same size, okay? And then if I apply multiple convolutions, so here I have another convolution, maybe I'm going to do this, right? Here, then this is going to give me another output image like this. And all this is going to be my next image of images, right? Or my next layer, if you will. That represents what I have done. And then what I'm going to do, I'm going to treat this as a new image, right? And I'm going to apply convolutions here again, right? So I'm going to take a window. I'm going to apply a convolution with a kernel, a selected kernel, and I'm going to get a new set. Actually, let me draw this like that. Like this one, and then I can do this like this, and I get an even larger result, right? And then, of course, this grows exponentially large, right? And you go on like this. And that's the idea of the mammalian visual system that starts with some information here, right? And it keeps processing it in multiple ways using those filters, so to speak, right? Those center-surrounded filters that I described, right? Which to us are just going to be described as a simple convolution, right? In fact, most people describe it as a correlation. But, well, that's how it's implemented. All right. So then that's what it was defined in the 70s or so. And then by the mid to late 1990s, people started applying backpropagation to learn the parameters of that network. Okay? And that's what we now call the convolutional neural network, or ConvNet for short. The most famous one of them is commonly referred to as AlexNet, because what was one of the first networks that really worked on very large data set, large problems. And people call it colloquially AlexNet because the first author of the paper that was published to describe this, Alex Khrushchev, it's called Alex, right? So, okay. So, how are we going to build these things? Because obviously, I'm just giving you here an idea, but how do people build this, things like the AlexNet? So let's define the types of layers that people use in a convolutional network, or ConvNet. Okay, obviously there are the convolutions that I have described here. Okay, this is very common. It used to be very common here at the end to have what's called fully connected layers. Now, what's the difference? The difference is the following. Note that here, each node of this layer sees only, or is only connected to a small number of nodes from that previous layer, right? Same here. This one is only connected to some nodes from the previous layer. Fully connected means that each node in that layer is connected to all the nodes in the previous layer, right? So that's obviously a possibility to have fully connected layers. Convolutional layers that we have already introduced. And then for a convolutional layer, obviously, you need to define the filter that you're going to use, or the type of convolution that you're going to use. Now, two things that I want to note when you apply these correlations or convolutions is this is an image in 1D, meaning a matrix, that has the values of what's called the luminance, right? The luminance is what you see when you convert a color image into black and white, right? Or grayscale. But if you have color images, then in computers, this is generally represented as RGB, And again, if you've taken my image processing, you know there are other ways to represent this. But you either have only color information, which is 2D, not 3D, 2D, plus luminance, in which case then you have 3D, or you have a 3D representation of both luminance and color combined, like RGB, okay? So in that case, you have 3 images like this, in which case this is treated as a tensor, not as a matrix, right? Well, a matrix is a tensor, but it's a 2-dimensional tensor, right? Or a tensor of rank 2. This is going to be tensor of rank 3, right? And the same can be done here, because when I do this convolution, right, throughout, and then I do another convolution with another kernel and so on, instead of creating a huge matrix, what I'm going to do, I'm going to represent this as a tensor, right? So every time I do a convolution, I'm going to have a new dimension or a new matrix in that extra dimension, that third dimension of my tensor. So at the end, we're going to apply tensor multiplication, right? Okay. How are we doing? Am I being told that it's time? It is, right? Oh, yeah, perfect. Wow, you guys are like at the second. All right, I'll continue from here next week. I'll see you next week. Have a good weekend.